In this video, we're now going to talk about scientific notation. As a note, understand that this concept of scientific notation is found in chapter 1 in the textbook. Scientific notation is a method that is used to express very large numbers or very small numbers in scientific measurements or calculations. If we look at the image of the slide, this is actually illustrating a person, and we are focusing specifically in their hair. On average, humans have 1 times 10 to the 5 hairs on their scalp. So what that means in terms of regular notation is that if we have 1 times 10 to the 5, this is 1 with 0, 0, 0, 0, 0. This is going to be 5 zeros. So this is actually showing that on their scalp, on average, humans have specifically 100,000 hairs on their scalp. Now, scientific notation is this method that we utilize to express the regular notation, which is here. Now, to show you a number that is very small, it says that each hair is about 8 times 10 to the 6 meters wide. So if I take this measurement in scientific notation and put it in regular notation, this means that the number is 0.0000008 meters in terms of its width. As you can see, this is a very small number. Now, how did I know to write those numbers in regular notation, and how did that transform into scientific notation? Let's explore how to convert numbers from regular notation to scientific notation and vice versa. So if we have a number in regular notation, you are going to see in those measurements all of the digits with all of the numbers that we have, and we're going to see the significant figures that those measurements have. You can see that on the left side of the slide, we have a guide in order to take a number in regular notation and convert it to scientific notation. You can see the different steps. I'm just going to generalize them and write them in order for you to observe how we obtain scientific notation for large numbers and scientific notation for small numbers. Let's first deal with large numbers. We can see the digits 2,400. Just from the discussions that we have previously, take a moment, determine how many significant figures are in the measurement 2,400. Now, when it comes to these digits, even though we don't have a decimal place that it is written, we can actually, partially, for the purpose of conversion to scientific notation, write the decimal place that it is implied. That decimal place that it is implied specifically for large numbers is at the end of all the numbers that are illustrated in the measurements. Now, according to the rules for writing scientific notation, we need to move the decimal place such that the coefficient is at least 1, but less than 10. We can see that on step 1. So if I move that decimal place, I need to convert it to a digit that is at least 1, but less than 10. In order to do that, I'm going to move this decimal place 1, 2, 3 places. Now it's going to live here. So that's why overall, we observe that this 2.4, which is the two numbers that carry meaning, are placed as the coefficient. And with that, we are meeting step 1. Because overall, since this has 2 sig figs, the coefficient must have 2 sig figs. Then, since I move the decimal place from right to left, my exponent for the power 10 is going to be a positive value that is specifically illustrated by the places that I use in order to move that decimal place. So in order to take 2,400 to scientific notation, its correct way to illustrate it is 2.4 times 10 to the 3. What about if we have a small number? It is in a small number. We have specifically the decimal place written. But remember that those zeros before the 8 and the 6 are just placeholders. They're placeholders essentially because they're showing you that you have a small number and they are not after the first non-zero digits, since they are before, that's why they are just placeholders. They do not carry meaning. They're just telling you that you have a small number. Now, since we have a written decimal place, then we have to take into consideration that for that, we can actually move that decimal place to meet that step 1. If I move that decimal place that is written in order to create a digit that is at least 1 but less than 10, we have 1, 2, 3, 4 places that we're going to move that decimal place. And since our measure number has 2 sig figs, that coefficient needs to have 2 sig figs. And then now it converts to 8.6. Now, since our movement of the decimal place for a small number is from left to right, that means that my power 10 exponent, it is negative. And again, it illustrates the places that I move that decimal place. Let's take a moment and actually do some practice problems in order for us to understand this concept. These problems are from page 49 in the textbook. Specifically, you see problem 1.26 and 1.28. In problem 1.26, we have to write the following numbers in scientific notation. So let's actually do together letter E and letter F. On letter E, we observe that that is a small number. In the case of small numbers, we need to take that decimal place and move it 1 time, 2 times, so we create a value that is at least 1 and less than 10. That means that 0.024 turns into 2.4. We're going to do the times 10. Since this started as a small number, we're going to do negative. And then, since we moved it 2 places, we're going to do negative 2 as the exponent to the power 10. Understand that if you start from the point of view of the scientific notation and then you have to compare regular notation, that's what we're going to do in problem 1.28. Let's proceed to look at letter F on problem 1.26. If your measurement is 1,500, there's no written decimal place, but we know that there's one that it is implied because this is a large number. And that decimal place lives at the end of those digits. So we write it right here. Now we're going to move that decimal place 1, 2, 3 times. So that decimal place will be there. So that means that that number becomes 1.5, and we're going to do times 10. Since we move 3 spaces from right to left, that means that this is positive 3 when it comes to the scientific notation. Take a moment and practice with letter B and letter C. Let's now do problem 1.28. It asks, which number in each of the following pairs is smaller? The numbers are given to you in scientific notation. So if I need to compare the two numbers on letter A, which is 0.9 times 10 to the negative 3 versus 5.5 times 10 to the negative 9, I can take those numbers and change them from scientific notation to the regular notation. So since my exponent is to the negative 3, let's understand that what I'm going to do is take that 0.9, and then since it's times 10 to the negative 3, I'm going to move that decimal place 1 time, 2 times, 3 times. Since I open 2 pockets, I'm going to populate them with zeros. And this is the conversion from scientific to regular notation. So let me just write it here. So students are not confused. So that means that the value 0.9 times 10 to the 3 is actually 0.0009. Then, in the measurement 5.5 times 10 to the negative 9, this means that I will take that 5.5 and I'm going to move that decimal place 9 times. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now the decimal place is there. We can see that that opens the pocket for 1, 2, 3, 4, 5, 6, 7, 8 zeros. So that number becomes 0.1, 2, 3, 4, 5, 6, 7, 8, 5, 5. So that is the regular notation. So when we compare these two, we can observe that this number, it is smaller because the quantities of the zeros that are preceding the non-zero digits. What is the shorthand when it comes to an exercise like this? Well, you can always verify your work by doing what I expressed here, or what you can do is looking at the exponent, and in the case that the exponent is negative, the larger that negative value, the smaller is the digit in regular notation. And then if you have things, for example, in letter B, where you have 1, 2, 5, 0, versus 3.4 times 10 to the 2. This is already in regular notation, so we don't have to do anything. If we have the number 3.4 times 10 to the negative 2, what we do is that we take 3.4 and then we move it 2 spaces. 1, 2. That pocket that we open, we populate it by a 0, so we're comparing it to 340. We can see that the smaller number in this case is this one. So since in letter B, one number was in regular notation and the other one was in scientific notation, you either turn both of them into scientific notation, look at the exponents, and then look at the coefficients, or sometimes you can just look at the exponent if you can already tell which one has the smaller coefficient. And then based on the exponents, you can determine which one is the smaller. So I would suggest that in order to practice, do problem C on 1.28 and determine which one of those two values is actually the smaller number in the pair. Next topic that we're going to talk about is rounding. Rounding is something that we must do at times when we're doing measurements, but understand that when it comes to rounding, and these numbers may be after we do calculations with our calculator, we may have to round to a specific number of sig figs. Rounding, we can see the rules on the left side of the slide. You're underlining the digit, then you're going to look next door, meaning the digit that you have to the right. If it's 5 or greater, you add 1 more to the number that you underline. If it's less than 5, you do not change it, okay? At times, we may have to change everything to 0, but it depends on the case. In order to practice this concept, let's do problem 2.23 on page 65 of the textbook. The problem reads, round off each of the following calculator answers to 3 significant figures. When it comes to this, let's practice together. Letter A. Letter A says that my measurement is 1.854 kg, which means kilograms. Since I need to round to 3 sig figs, I need to find from left to right, where are my 3 significant figures located? So when I do this, 1, 8, and 5 are significant. So 5 is the one that I'm going to underline. Let me highlight this again. And then I'm going to look next door to 5. So if I need to round this measurement to 3 significant figures, since I see that next door to 5, I have a digit that is less than 5, then that means that 5 is not changed. So rounding this measurement, I'm going to say 1.85 kilograms is my final answer. At this time, practice by taking letter B, that measurement that is illustrated there, and round it to 3 significant figures.